Hi everybody, in this video I am going to take you through various parts of a free response question involving an electrostatic cloud. What is an electrostatic cloud, you might wonder? Well, let's take a look at what we're going to do. Alright, so here we have a spherical cloud of charge radius big R contains a total charge plus Q with a non-uniform volume charge density that varies according to this equation. And it works as long as we stay inside the cloud. Outside the cloud we have a charge volume density of 0. All right, so little r is the distance from the center of the cloud expressed following algebraic answers in terms of big Q, R, and the fundamental constants. All right, determine the following as a function for R. For R greater than big R. Okay, so that means we're outside the cloud. It says the magnitude of the electric field. All right, so I've got pages that breaks this up just so we can focus on one page at a time. All right, so for part A, we want the electric field where we're outside the cloud. So, so anywhere out here, out here, out here, here, anywhere we want, as long as we stay outside that cloud. All right, so for electric field, we're going to use Gauss's law. Okay, and our intuition for this hopefully leads us to see that outside the electron cloud, here, let me finish writing Gauss's law here, that as long as we stay outside this thing, okay, well then we have the entire charge contained within. So that little Q inside there, all right, is our entire plus Q. All right, and so if we take and we evaluate, all right, so our little Gaussian surface here would be the sphere that goes around the outside like that. Perfect sphere. I'm not even going to bother to draw this because we've seen this before. All right, so the surface integral, so it's a 4 pi r squared, okay, is the integral surface, closed surface integral of the area function, all right, is equal to plus Q over epsilon naught. All right, and so they're not surprisingly, at least I hope it's not surprising at this point, that is, as long as we stay outside the cloud, okay, from the perspective of point P, it's going to see it or feel it like a point charge. So we just get this Q. I dropped the plus because it's implied. 4 pi, I'm going to put the epsilon naught there, and then r squared. Okay, so pretty much your classic Gauss's law problem for while we're outside of the cloud. It just appears like a point charge. Okay, great. Now what? Part B, a proton is placed at point P shown above and then released. Okay, describe its motion for a long time after it's released. All right, so I just put a little positive charge there just to help us visualize it. Remember that this electron cloud, or excuse me, this charged cloud has a positive Q in there. Okay, so because like charges repel, the little proton is going to be repelled away from the electron cloud, and it's going to follow the electric field strength here, but the repulsion really is, that's the force, right? So just think, the force that acts on the charge, all right, which comes from, so the electric field is defined as the force on some little charge, all right, and so if we go Q times E, that's our force, where our electric field is really just this Q over 4 pi epsilon naught r squared. Okay, and so if I took that and I multiplied that by Q, well, what I really have here is that I have this, what would that be here? So that'd be big Q times little q over 4 pi epsilon naught r squared. Okay, what we're really looking at here is that's just Coulomb's law. Remember, 1 over 4 pi epsilon naught is k, so what we really have is the force is equal to k times the charge of the cloud, q1, times q2 over r squared. Okay, so these are the same formula. All right, so the point of all of this, all right, is, I should have changed colors here. Let's be fancy, and we'll just do each one in a different color. There we go. So we'll use blue. Sorry. So anyways, the point is that this force function that we're looking at, well, k is a constant, or if you leave it as, 1 over 4 pi epsilon naught, it's still just all constant, just some number. All right, and the cloud has some overall charge, big Q, that's our Q1, and then the little Q2 or little q, that's the proton. Okay, so the point is all this stuff is constant except for that r squared. So we say that F would be like proportional to 1 over r squared. Okay, and well, by Newton's second law, force is equal to mass times acceleration. Okay, so we can say the same thing as force is proportional to acceleration. And so the acceleration is proportional to 1 over r squared. So as r gets bigger, the acceleration is going to get smaller by a factor of that distance r squared. Okay, so now what would that look like on a graph? All right, well, if I graphed out an acceleration versus distance graph, okay, so acceleration versus r, all right, it would follow that decaying kind of exponential shape. It will look, something like that. Oops, let's see here. Don't want to make it seem like it. There, that looks a little better. Okay, so that kind of decaying exponential. Now it says describe its motion for a long time. Okay, there. So because it's talking about time, it's probably more appropriate to look at this as an acceleration time graph. All right, as the distance, it's going to take time for the thing to move away. All right, so it would follow the same basic kind of relationship if we had like an AT graph. All right, and well, acceleration is related to velocity, and that acceleration is the slope of a velocity graph. So then the velocity graph, we could actually figure out what that would look like too. Oh, so much good review in this question. Okay, so if I looked at the corresponding velocity time graph for this thing, all right, well, my acceleration is a positive value, something greater than 0. Okay, it's just getting smaller. Okay, so that means that the slope of my velocity graph is greater than 0, so a positive slope that's getting smaller with time. So that would look like this. Okay, the velocity graph is approaching some finite value. When is that value actually become finite? Well, really, it's not until that r value goes to infinity. So it's going to move away. As it moves away, it's going to be moving with a really large acceleration to begin with, and then as time goes on, the value of that acceleration is going to get smaller and smaller and smaller. It's going to approach a constant velocity. Okay, so we wouldn't have to write down all the mathematics, but it's a good way to kind of reason it through and see where all this stuff comes from. All right, it would move away while speeding up, but the rate of speeding up would decrease, eventually becoming constant at distance infinity. Okay. For part C, what are we doing in part C? All right, so now we're going to take an electron. Okay, so I've got my picture here where I've placed the little proton with electron of magnitude E is now placed at point P, which is a distance r from the center of the sphere, and release determine the kinetic energy of the electron as a function of r as it strikes the cloud. Okay, so an electron of charge magnitude E. All right, so the fact that they define that as magnitude E tells us that's a legal variable, and if I were to look at the AP equation sheet here, just so you can see this thing. Okay, so E is up here as well. As you can see, it's electron charge magnitude 1.6 E times 10 to the negative 19th coulombs. Okay, so that's fine. So I can use that if I need it. But we're just looking for an expression with symbols, so we're allowed to leave it as E, just like, we could write potential energy as mgh. Okay, we could leave the G in there just written as a fundamental constant. All right. Well, anyway, so it says to determine the kinetic energy of electron as a function of r. Okay, where r is distance. All right, so energy and distance. Okay, so for me, the way that I would think about this is the definition of work is the change in energy. So see, like this is a positive charge here, right? And if we release it from point P, well, what's going to happen is it's going to be attracted to the cloud. Okay, it's going to be pulled towards the cloud, and as it's pulled towards the cloud, it's going to speed up at an increasing rate, but the point is it's going to speed up. So it's going to gain kinetic energy as the the electron, pardon me, is pulled towards the cloud through this electrostatic attraction, okay? And so the work that gets done on it is going to be the force that's applied to it over some displacement. That's kind of like the secret to this. But of course, the force varies with distance, okay, as a function, all right, from Coulomb's law. That's really what this is all about, is up here, this Coulomb's law. So I need a way to relate that. And since it's a function, that gives me the hint that some kind of calculus is going to be involved. So if I'm not really sure how to set it up or what to do, okay, well, just like I went to the AP equation sheet to look and find that E value, I'm going to poke around here, all right, and see if there's anything that's going to help me figure out how to set up my calculus. Okay, and so if I look around here, I see, oh, hey, look at that. The change in energy is equal to work, and that's equal to the integral of F dot dr. That's the key right there. That's exactly what I'm going to use. So let me jump back over there. Okay, so, all right, the change in energy, in this case, kinetic energy, is going to be equal to the work, which is equal to the integral of F dot dr. All right. Now, if I just take this little electron, I put it at point P and I let it go on, like I'm releasing it from rest. So the point is, all right, I'm looking at the delta KE here. So it's like KE final minus KE initial. So the change in kinetic energy is going to be equal to this integral of F dot dr, where that initial kinetic energy is 0. So I can just say that the kinetic energy that the thing gains is equal to the integral of F dot dr. Okay, where that F, that's just the electrostatic force. That's Coulomb's law. All right, which if we wanted to pull it off the AP equation sheet, it's written in terms of 1 over 4 pi epsilon naught Q1 Q2 over R squared. Or if we just remember that that's equivalent to K Q1 Q2 over R squared dr. Okay, and a couple other things. So we want to get an expression in terms of big Q's, little big R's, all the allowable variables. Okay, so I'm just going to take and I'm going to rewrite this one more time because I don't want to mess this up later. Okay, it's the integral of K. All right, so let's say Q1 is the cloud. Okay, so the cloud has charge plus Q, and Q2 is going to be the electron, which has magnitude E. All right, so plus Q, so that's just like capital Q times E over R squared dr. All right, and then I'm going to pull out all the constant stuff that I don't really care about. So that's K, big Q, little e, times the integral of 1 over R squared dr. I like doing that. It just makes it easier for me to see what I need to do in terms of the calculus. All right, and then what are my limits of integration? So it's an electron of charge magnitude placed at point P. So we're going to start at point P, which is a distance R from the center to release. Determine the kinetic energy as a function of R. Okay, that's the key. It's a function of R. So if I start at point P, okay, and I go to some location R, okay, so I'm going to keep that as a little r because I want to know anywhere in between here, okay, point P and the surface, what's going to happen. All right, and so there's my integral. So that's what I'm going to integrate. So I get this K, Q, E, and let's see, the integral of 1 over R squared is negative 1 over R, evaluated from point P to R. All right, so that kinetic energy is just going to be equal to K QE times, let's see, so it's 1 over P minus negative, a lot of negatives. Actually, I'm sorry, that should not be 1 over P, that should be 1 over R. Excuse me, so negative 1 over R minus 1 over P. Geez, what a mess. All right, and then, so that gets me KE is equal to K, QE, and let's just flip that over. So that'd be negative 1 over P, and then that would be minus 1 over R. Okay, so this is the answer for the kinetic energy, all right, that it has. Just as a quick check, all right, it's supposed to gain kinetic energy. So basically, if I just want to make sure that I set my integral up right. So if I just think about this logically here for a second, okay, so point P is out here, and then the little r would be, like some r in between here, right? So the little r would be less than the P. So just like mental check, okay, so like little r is less than P, all right, which means that 1 over P is going to be bigger than, or excuse me, 1 over P is going to be smaller than 1 over little r. So I got a smaller number minus a bigger number. So that means that this right here, this is negative. Okay, what's inside the parentheses is negative. All right, and let's see what else I'm going here. K is a constant, that's 9 times 10 to the 9th. Q is the positive charge, okay, of the cloud, and this is the electron, okay, which has a negative charge. So I'd have a negative here, and I have a negative in the parentheses. I get a positive kinetic energy. I'm pretty sure I set my limits of integration up correctly, set up my function correctly. All right, I'm good. I'm moving on. All right, let's see what we got next here. Part D, we're supposed to derive an expression for rho naught. Okay, well. All right, so that's the volume charge density. Okay, or at least the initial volume charge density, where the volume charge density is given a function of rho naught and 1 minus little r over big R for as long as we're inside the cloud. Okay, so where do we even start this? With the definition of charge density, okay, or volume charge density. Okay, so then this rho is just equal to whatever charge we have in this thing divided by the volume. Okay, so then if I take and I move over the volume, okay, this is going to be equal to the total charge. And I'm starting with that because I know the total charge. Um, the rho varies as the volume varies. Okay, so that's kind of the secret here. So we get little slices. If we took little slices moving from the inside of the cloud to the outside of the cloud, we get little like DQs that would be summed up as we would sum up the volume. All right. The secret is that this, as the volume changes, it changes as a function of R. Okay, whereas this rho value also changes as a function of R. So we need a way to account for that. Okay, so to do that, we're going to take a quick little aside to kind of know how to think through this. So here, an aside. Step over here. All right. Many of you may have noticed that for a sphere, all right, the surface area is equal to 4 pi r squared, and the volume is equal to 4/3 pi r cubed. Okay, these two things are related to one another, and those of you who are kind of mathematically good at calculus, you can kind of see the pattern here that the volume is the surface area, or is the integral of the surface area. So now what gives? What's that all about? All right, well, we're talking about a sphere here, so it's a two-dimensional drawing I'm about to make, but imagine in 3D, if I just took a teeny tiny little piece of a sphere, it'd be like a little, we'd be looking at the surface area of like a little ball, okay? Well, if I moved from the inside of the cloud to the outside, okay, I could slice that up and then add together the little infinitesimal little slices, almost like the layers of an onion, okay? And as I built up each of these little infinitesimal surface area pieces, I layered them one on top of the other, I'd be gradually building up the volume, okay? So again, I think that onion analogy is probably a really good one in this fact. So like, the little slices of the onion, the little layers of the onion, that's the surface area as they get it added up to make the volume. All right, so point is that to get to this volume, okay, I'm really just going to take the integral of the surface area with infinitesimal little chunks, right? I'm going to sum up the infinitesimal little chunks moving from the center out to whatever radius I want, and that would give me the volume. So then the volume is just equal to 4 pi r squared dr integrated from 0 up to, well, whatever radius that I want. All right, and if I took the integral, right, the 4 pi, that's just constant, so it's really just the integral of r squared, which is r cubed over 3. And if I have 4 pi r cubed over 3, hey, look, there's our volume formula for our sphere. Okay, so that's kind of the trick there. So to use this in our problem, okay, well, we've got this written in terms of dv. Okay, so then dv, so I'm going to ditch that little integral sign just for a minute, just so we can do a substitution. 4 pi r squared dr. This is really what is going to get subbed in back to this original idea. Okay, so I've got this rho times my dv, which is the 4 pi r squared dr is equal to dq. Okay, and I'm doing this because this now allows me to write a function with r, okay, that I can then integrate. The key being is that rho is a function in terms of r that contains rho naught. So I can get the rho naught into my expression. So that rho gets replaced by rho naught, 1 minus little r over big R times 4 pi r squared dr is equal to dq. Okay, this allows me to now have an expression that I can integrate, because everything is in terms of, has all the little r's in there, and it's going to allow me to eventually solve for rho naught. So I'm going to take the integral on both sides. All right, what the heck are my limits of integration? Okay, well, on the right side, it's easy. I start from the center and I move out, all right, to some overall charge Q, okay, whereas on the left side of the equation, I start at a distance of r from the center, and I go all the way out to the actual radius of my charged cloud, okay? So what do I have that I can pull out of the integral sign? So I got rho naught, that's something. I can pull out the 4 pi. Probably should have put the 4 pi in front, but whatever, it doesn't matter. So then it's from 0 to r. So then let's see, what do I have left here? I've got 1 minus r over r times r squared. So 1 minus r. Take my time here because I feel like this is an algebra mistake waiting to happen. And here, move that up there just so that it doesn't look like it's in the function because there's already too many r's in here. R squared dr is equal to 0 to q dq. All right, so then I'm going to bring that 4 pi out in front of the rho naught, 0 to r. All right, so then let's see, that'd be r squared minus r cubed over r dr is equal to 0 to q dq. I don't know why I keep writing this. We know what's on the right-hand side. It's just q. Okay, so then let's just go ahead and do that. So 4 pi times rho naught. All right, so then the integral of r squared would be r to the third power over 3 minus, let's see, so it'd be r to the fourth power over 4 with that extra r in there. Evaluated from 0 to big R is equal to, all right, I'm skipping steps on the right side. It's q, evaluated from 0 to q, so it's q. Okay, and, oh, hey, look at this. This is kind of nice. All right, if I evaluated this for 0, there's nothing. Okay, so actually, this is actually not simple, I wouldn't say, but at least I don't have to plug in some stuff. Okay, so there we go. I can work with that. Yeah, that's not too bad. That's not too bad at all, in fact. Okay, so then can we simplify this at all? Yes, I feel like we can. Oh, wait a minute. Silly Zarzak. From 0 to r, these are capital R's. I don't know why I erased that parenthesis. So this would be big R to the third power, big R to the fourth. Yeah, actually, we can. Yeah, this simplifies down. There we go. So 4 pi rho naught. So then I have r. So let's r to the third power over 3 minus. Oh, look at that. That simplifies down to r to the third power over 4 is equal to q. There we go. All right, now we're making some progress. So 4 pi rho naught, pull out an r to the third power. That leaves me with 1/3 minus 1/4 is equal to q. Let's see, 1/3 would be 4 over 12. 1/4 is 3 over 12. So 4 over 12 minus 3 over 12 is 1/12. Okay, 1/12. All right, hold that in your brain. So 4 pi rho naught r to the third power times 1/12 is taking and dividing this by 12, which is q. All right, so that gets me, what is that? Just rho pi rho r to the third power over 3 is equal to q. Okay, and all this was done to derive an expression for rho naught. Okay, so then rho naught, see, so multiply over the 3. So 3q divided by pi times r to the third. There we go. We now have an expression for rho naught. Yay! Hopefully that's the end of the problem. Oh no, there's another part. Okay, great. What do they want now? Determine the magnitude E of the electric field as a function of R for R smaller than big R. Okay, magnitude of the electric field. It's got to be Gauss's law. I'm just going to write it. EDA is equal to Q over epsilon naught, where the Q, so is a function of little r for little r less than big R. So we're inside the cloud, so we've got some little charge enclosed. All right. And we want as a function of r, okay, a function of r, calculus. Okay, so then what we really need is to get the electric field as a function of r. We really need to now know how does the charge inside our little Gaussian surface vary as a function of r. See, because it's not constant inside anymore. Okay, it follows this thing. All right, so we're going to have to play around with this charge density. This volume charge density idea again. Okay, so over on the side here, so the volume charge density is equal to the Q enclosed over epsilon, or not over epsilon, not over the volume, where the volume we're talking about now is the volume that varies with some little radius. Okay, it's whatever volume for whatever little radius, as long as we stay inside this Gaussian surface of the sphere. Okay, great. So rho times VR is equal to the Q inside. Okay, so we're going to again play this game. Okay, except now we're talking about the little q. All right, so rho dV is equal to dQ. All right, and just like we did before, okay, this dV is just going to be the 4 pi r squared, which is the surface area, times dr. So it's another way you can write dV is equal to dQ. Okay, and that's really the trick here. All right, is that this Q up here is it's actually a dQ. Okay, it's a function of Q, and don't worry, we'll evaluate the function. All right, we're going to do the integral so that we can get the full Q. So let's just go ahead and deal with it and do it. All right, so then E dA is equal to this mess right here. I'm going to copy it. I'm like afraid now that I'm going to make an algebra mistake. Okay, so this mess here over epsilon naught. I'll write that part. Great. And the rho is this function. Oh my goodness. Okay, so I feel like I'm going to need some more space here. So E dA is equal to rho, where rho is equal to rho naught. 1 minus r over r times the rest of this. So 4 pi r squared dr over epsilon naught. Okay, and I'm still not going to integrate yet. All right, because I have a function for rho naught. That's what this is here. Because I have to write this expression in terms of the given variables and fundamental constants. So E dA is equal to rho naught times 1 minus little r over big R. It's 4 pi r squared, all that over epsilon naught dr. What a mess. Before we go any farther, okay, avoid the temptation of trying to do anything with that EDA on the left-hand side. Okay, we have to take care of what's on the right-hand side, which is I need a function that describes the charge as it varies with radius divided by epsilon naught. Okay, I have to have EDA is equal to Q over epsilon naught before I try to evaluate the surface integral. Okay, Gauss's law says you can find the electric field by evaluating the surface integral once you know your Q and your epsilon naught. All right, so leave the dA alone, or else it's not going to work. Okay, so is there anything that we can do over here to simplify this? Oh, look, we can cancel out a pi. Great. Awesome. Anything else we can do? Let's see. So I got a 3 coefficient, a 4 coefficient, so I got a 12. All right, that's something, I guess. So I got 12q over r to the third power. All right, this times, let's see, let's distribute the r squared. So what is it? That's r squared minus r to the third power over r dr over epsilon naught. Okay, I guess I could have pulled that epsilon naught. I will here in a second. All right, so I think I can finally integrate. Yes, I can integrate. Oh boy. All right, so E dA. Okay, so then 12q over epsilon naught r to the third power. All right, times the integral of this. Boy, I hope I didn't forget anything. Okay, so now we need the limits of integration of this. All right, so what's this all about? So back up here. Determine the magnitude of the electric field as a function of r. Okay, as a function of little r. Like, yes, it ends at big R, but I would need an electric field that's described for any r in between. So the limits of integration go from the center of my cloud out to some arbitrary radius not larger than the big R. Yep. Okay, so there. Time to actually do the calculus. Okay, so I got r to the third power over 3 minus r to the fourth power over 4r as evaluated from 0 to little r. Okay, so let's see. So if I plugged in zeros, I don't get anything. All right, so then it's really just plugging in little r for little r. Great. Okay, so this mess here really just says EDA is equal to all this is Q. Q, 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 Q. All that describes Q over epsilon, and that does too, over epsilon naught. Okay, it's really just large Q times some weird function with little r's and big r's over epsilon naught. Great. Let's do Gauss's law. Okay, as we move from the center outwards, 4 pi r squared is equal to this. Yep. Okay, great. Is there anything I can do with this mess? Yes. Yes, there is. Let's see, what can we do with this mess? I'm going to take and cancel that, so then that becomes r to the first power, and then that becomes r to the second power. That's not bad. Okay, let's see. So if I divide it over the 4, that'd be, take that, and that would be 3. Okay, and then I've got a pi as well. I left a little knot off the epsilon. I don't know where that went. Okay, so then here we go. So E is equal to 3Q over pi epsilon naught r to the third power r over 3 minus r squared over 4r. And I think this is the answer. Okay, so electric field, so Q is a given value, epsilon naught and pi are just constants, 3 is coefficient, R, big R is okay. I see big R again, and little r is as a function of R. I think this is correct. Now, if I'm not sure, I've done all this math, I'd like to know if it's right or not. So one way that we can check, okay, is as we look at the end of it. So when little r becomes big R, what happens? Okay, so then bring this down. Okay, I just don't want to write all of it again. I feel like I've written this so many times. Oh, no, not that. Let's make this black just so we're just doing this to compare an answer. Okay, so when this is a big R and this is a big R, okay, what does it simplify down into? Let's find out. Okay, so then what can we do with this here? So we can get rid of that. Okay, so then I've got R over 3 minus R over 4. All right. So then keep all that. I'm going to factor out like a big R. So 1/3 minus 1/4. Okay, so then I can take and not cancel, but I can reduce that down. All right, and so I get E is equal to, let's see, so that's 3Q over pi epsilon naught R squared. Again, this is just checked. I've done this much math, so I might as well keep going. Okay, so then let's see. So I've got 1/3 minus 1/4, so that'd be 4/12 minus 3/12 is 1/12. That's what's inside the parentheses. Okay, and that means 3 over 12 is equal to 1 over 4, right? Reduced, yes. So I have Q over 4 pi epsilon naught R squared. Okay, so what does this mean? This means that once I get out to the edge of this charged cloud, once I'm out there, then anything beyond that, it looks like a point charge. And what is this? This is the electric field around a point charge. Remember, 1 over 4 pi epsilon naught, that just equals K. So this really just says KQ over R squared. I'm pretty sure we did it right. This is the answer for party. That's my story. I'm sticking to it. Thank you for watching. This is Mr. Zardik saying, I'll see you next time.